Hello all and welcome to my YouTube channel. So today in this particular video we are going to discuss about a paper called Clip from OpenAI. So this is an amazing paper and it's an amazing development in terms of learning and image embeddings and language embeddings together in a same with the same model and understanding how we are able to do it without using any labeled data. So here we are just using self-supervised learning to train the language model and the image model together and learning the behavior of it using the image and language together. So that's what the clip is all about, and we'll dig a little deeper into understanding of this clip paper, and we'll try to also see the implementation of a particular clip model. So right now whatever you can see on the screen is it's an uh, it's an official implementation of a clip from OpenAI. So you can go through this particular repository to understand the things, how the things have been given here, and you can go and check their blogs and understand the things. Even they have given the paper, and you can use the collab to just run up their implementations, whatever they have done. So this is just an implementation of a particular clip that has been given in this particular GitHub. So we'll just go through this clip paper, and we'll just then after that we'll just go to the implementation of this clip, and we'll see how these things have changed, how we are able to train image and text together, and we are able to get the nice embeddings without the labeled data set. So it's just like a supervised self-supervised learning that is being taken care, like the BERT model have been trained, right? So it's just like a similar training, self-supervised training, without using labeled data, and it is being trained without being much interference, worrying about the labeled data. So it's just a awesome implementation and awesome learning. So we'll just look upon it, and we'll discuss upon the things. And if you have any doubts regarding this particular implementation or any of the understanding, you can just mention the things in the comment. I will try to reply into this, right? So let's now jump to the paper, and we'll just discuss the architecture, how it looks like. So this is just an official implementation of a clip, or the of official discussion where the clip model has been explained. So you can just check out this particular clip paper, and you can go through this clip paper. It has been amazingly explained here how the things has been done. So I will try to explain the things at a very high level, but it is very it will be very good to uh, reach out or read the things in a very detailed manner. So I will highly recommend you to go through this paper, and it will make you understand many of the things, and it will clear the things so very well. So now let's move to the architecture part, like how this clip and how this image and text training are being done without using any label, right? So you can see this is an architecture, right? So what is happening here? If you see, you go through this particular you can see this is a text encoder, and here is a image encoder. So text encoder is nothing but there is some model called BERT model, or any model like Roberta model, or any language model, whichever you want to use, you can use it here. So this is just a text encoder where you will input your all the text, and it will generate an embedding for you, right? And similarly, even you can see here is an image encoder. There's nothing but you can use CNNs here, and you can use visual transformers, which will do a similar kind of thing, where it will take an input as an image and it will output as an embedding of particular image. So this is what text and image encoder is that do this is what the function of the text and image encoder. So now why we are taking this text encoder and image encoder, right? So obviously we cannot pass text and image as it is, so we have to encode it. So if you use a text encoder as a bird, so it will take up the text and it will encode into the respective embeddings. Then it will output something some different dimensions, right? So this dimension of this particular bird encoder would be like 768 dimension of particular word. And similarly, if you check out this image encoder, and if you're using CNN network to encode your image, then their dimension would be differ, right? So if you're using ResNet 50, their dimension would be 2048. And if you're using VIT transformers, their dimension could be different, right? So depending upon the image encoder and text encoder, the output of the text encoder and image encoder will differ. So what happens here is they use a BERT encoder, and they use VIT transformers and ResNet 50, whatever model you want to use, or even they used different varieties of model over here. So they have taken up these models, and once they have done it, once they have passed the text into the text encoder, and once they have passed the image to the image encoder, then the embedding of this particular text encoder will be different, and image encoder will be different, right? So to bring up that into a similar space or similar embedding space, they have pass this particular output of this text encoder and image encoder into a projection head. So what does that projection head means is it's just a ANN network that will take up these embeddings, and it will project into the similar dimension space. So what does that means is that when we talk about the output of this text encoder, so they will pass it to the neural networks or simple ANN networks or multi-layer perceptron, where it will convert into a single dimension network. So let's say 256 dimensions, right? So let's suppose the text encoder has outputted 768 dimensions, so we are compressing it to 256 dimensions. The output of the text encoder, we are compressing it to the 256 dimension by using the ANN network. Similarly, we are using image encoder, and we are passing it to the ANN network to compress into the 256 dimensions. So then once we have this dimensions equal, like the text encoder and the image encoder dimensions are equal, then we can use something called similarity, calculate the similarity between the text and the image, and then that's how we're gonna learn the relation between the text and image. So let's go to the next step. So this were the general philosophy that generally is being done. So now let me explain what happens once we have the dimensions on the similar space, right? So if let's suppose we pass an image, and we pass an respective caption, or we say the respective information of that particular image. So we have this dog image, and you can see there's a information about that particular image. So they said paper the Aussie pup, so it's just an information of this particular dog. So its respective image and its respective text is being passed to this text encoder and image encoder. And now we want to learn the similarity, or we want to learn the embeddings of this text and image, right? So how this is gonna be done is by calculating a similarity matrix. So if you see here, for each and every image, so this is image 1, image 2, image 3, and so on, and for each image we have text, right? So T1, T2, T3, right? So what we want to associate is, once we have the image embedding and text embedding, we want to calculate the relationship between these two. And obviously the first image and its respective text should have highest correlation, right? Because they are actually correlated, because this particular text is talking about this particular image, right? So this has to be highly correlated with this particular image, right? So that's what we are trying to learn here. It's just a dot product of this particular image embedding and the text embedding, and we try to learn the correlation between these two by using cosine similarity. That's how the loss function is also defined. So we'll go to that loss function, how that particular loss function is being defined, and how we are using to get this text and the image closest to each other in the real time. Although we know that this is related to this, but model doesn't know, right? So we want to make it sure that these two are related, and hence we are going to learn the embeddings and the information from the image as well as text, and we're trying to compress that into a similar embedding space. So we are trying to compress or find a relationship, or we are trying to relate the text and its respective image into a similar embedding space, and that's how you're going to learn it, learn the model. That's how the model going to learn the embeddings into a particular space. So this is going to be done by using different image. So if you see, let's go through this first line of matrix, then we'll go to the second. So what happens is, let's suppose this is the ith image and its respective text is t1, right? So what it is going to do is, it will try to learn the highest correlation or highest similarity between its image and its text, and it will decrease the correlation, or we can say the similarity, with other text images, right? So this is the t1 and this is i1, so obviously this dot product should be very high, and this t2 is this text is different image text, right? So the relation between this first image and this second image would be very less, and this and for the third image, sorry, for the third text and the first image, the relation should be very less, and likewise the others, right? So this is what we want to learn. We want to learn the similarity between the image and its respective text, and we want to decrease the similarity between the first image and the other text image, right? So that's what we want to learn. And similarly, if you go to the image 2, you can see the relation between these two, between the image 2 and the text 1, has to be very low, and image 2 and text 2 has to be very high, and similarly image 2 and text 3 has to be very low. That's how it's gonna be learning. So we want to focus on the this particular blue part, where it has to learn the closeness about this particular embeddings with respect to the text, and it should also decrease the similarity between other text of the images, right? So this is what it is. This is how the model is learning without any label. So it is itself creating a label for itself by taking this, by considering this as a positive sample. That means if image 1 and text 1 are related, so this is a positive sample for it, and t2 and t3 for the image 1 are the negative samples. So that's how it is creating a label for itself by using this similarity numbers. And if you want to dig deeper into the codes, so if you go scroll down into this particular paper, you're gonna see how the things have been implemented on the loss side. So if you go and see, here is the loss implementation. So if you go into this particular loss, so if you see, this is an image encoder that we have talked about in the particular image, right, at the top. So it takes up this image and pass into the image encoder. It will get the image embeddings. Then you pass the respective text of this particular image to the text encoder. It will give you text embeddings. Now what they do is, they just normalize this particular embeddings, whatever the embeddings you got from here. Why they do that? Because they want to make sure that the distribution is almost equivalent, because text encoder might give different distribution and image encoder might give different distribution. So to make it normalize, so to make it similar distribution, they are normalizing these two embeddings, and now they are calculating a dot product. So you can see it is taking an image and its text, and they're doing the dot product of it. So that's how they are calculating the dot product. And now once you have this dot product of the particular image, so if I have to go to the top of the image, that's what they are calculating here, the dot product. You can see, right, I of image 1 and text of 1. So that's what they are creating. They are calculating the image. That's what they are calculating the dot product with its image and its respective other images as well. So they are calculating the dot product from its text as well as dot product from other text also. That's what they are doing here. If I go head down, then this is the thing they are doing here, and then they are calculating the cost entropy loss functions, considering the logistics and the label. So that's a part of a contrastive learning. Whatever the dot product they have taken, so that becomes a predictive loss. So that becomes a predictive logics, and then they also take up this labels. So from where these labels are coming up, those labels are nothing but the positive samples and the negative samples they're gonna create, and they're gonna generate the self labels from here. So, and once this image loss and the text loss are being calculated, then they're gonna average this loss to calculate the generalized loss, right? So that's how they're gonna learn the embeddings from here. If you want to, like, if this has to be done using the code, It's very easy. It becomes very clear when you do the coding, but I will explain this once more when we go to the code, right? So that becomes very clear how we are actually trying to calculate the contrastive loss. So if I have to explain more on this, what are the encoders they have used? So they have used like they are using obviously BERT and the visual transformers to calculate the encoding. So if I go to down, and you can see they have tried many of the encoders for the image like ResNet 50, ResNet 101. They have also tried VIT 32 with VIT B16 and VIT L14. So they have tried a lot of text encoders and image encoders to encode the things and learn the embeddings by its own by calculating the similarity between each and every image and text pair, and also calculating the contrastive loss by using that correlation, right? By using that co-similarity. So that's an high level view of particular implementation of a clip, like not implementation, just a understanding of paper. Meanwhile, you can go through this paper and you can understand more of the importance where it went good. So there are other papers as well like Sim CLR and BITM. So these are nothing but image to image contrastive loss learning. So you can go through these papers as well. So these are the upgradation to the previous papers that has been done. Now previously they were doing just image to image similarity calculation, which was based on the contrastive law, which I have discussed just now. Now they are doing the same thing with respect to the image and text relationship. So if you go to this particular paper, you understand a lot of things. And what the model will output, the model will output the learned embeddings of an image and the text. So if your objective is to calculate or to get the nice embeddings of an image as well as text by using a single model, and that too they are two related to each other, then this is the model for you. So what you can do is you can just train a uh, image and a text. If you have an image and a text of a respective image, then you can train a model like a clip model, and you can get the embeddings of an image and text, and then you can use it as a classifier to classify it on anything. If you want to classify it on particular category, and you can do it for zero shot classification. You can do it for like you can take embeddings of this particular image and text that are related to each other, and you can do n number of things with that particular embeddings, right? So that's like an use cases that you can develop with this particular learned embeddings. And that too, you don't have to have a labeled data. It will create the data or label that the target labels on its own by taking itself as an by its text as by, like, let's suppose an image and a text have its image and text has its relation, right? So that becomes a positive sample, and other text of a particular image becomes a negative sample. So that's how it creates a target and the label for it to start understanding and decrease the loss. So that's how we do it. Now let me just go through the implementation of it, and things will become very clear. So this was just an overview understanding. So I found a very good implementation on the Kaggle with a clip implementation. So I'm just walking through you to it, and we'll just try to see how the things work, right? So uh, let me go through this particular implementation. What I can see on the Kaggle, I found this very useful. So these are just an simple imports. You can see they're using Distilbert and Distilbert tokenizer from transformers. So this is data. If you see this data, they have this image, the image and its respective caption. So if you see, there are multiple for this particular same image, we have multiple text associated with it, right? And similarly we have different images and their text associated with it. So what we want to do is we want to learn this relationship between this image and this all text related to this particular image. So that's what the embedding we want to create. So it will learn the embeddings of this image and this text together, and they also will learn the association between these two, image and text, right? So that's the importance of this particular contrastive learning clip paper, and we'll see how it works. So what we're going to do is we're going to take up these images and its text, and we'll try to encode it. So these are the configuration files. So what we are trying to do is here is we are just trying to associate the different parameters of a model. Like if you want to use uh, VIT, Resonant 50 or Distilbert, so these are the configuration files that they have mentioned. So you can use any of these things like VIT or Resonant or any of the like Google Vision's models, any of the models you can use for the image encoding, and you can use BERT model or Distilbert model or any other text encoder models. You can specify the models here, it will start downloading and it will do it for you. So right now, as an implementation, what has been done here is they're using Resonant 50 for image encoder, and they're using Distilbert for text encoding, right? So they're using these two models, and now they're using now the metric has been also being calculated. So you can just go through this metric, and now this part is for preparing the data set, like by using torch dataset. So to prepare the dataset, they're using torch.util dataset to prepare this class. You can just go through it. It's very simple. It's just not take much time to do it. So what ultimately is being done is they are taking up this file names. What are the file names you have provided, right? The image names and this respective text, and converting it to the PyTorch data loader. So that's what they are doing it here. And this is an image encoder part where we are loading the Resonant 50, and you are taking up their head of the model. That's what they are doing it here. So it will, if you pass this particular image into this particular model, it will encode the image. Similarly, they are defining the text encoder. They're taking the Distilbert and it will, they're freezing up the layers of the previous layer, and they're taking the output from this particular BERT model. And now this is a projection head that I talked about, where they pass this output of text encoder and image encoder to this particular projection head to reduce it to the same dimension space, right? To 256 dimension space. That's what they're doing it. This is just a normal AN network that they're passing it to, and will compress that particular text encoder and image encoder output into this particular dimension, right? So once that is done, we'll just collate this all things, image encoder and text encoder, into a single model. So you can see if you see they are loading up this clip model. Inside this clip model, they are loading up this image encoder, text encoder, and they're also taking this projection head, and they're passing this particular projection head of this image, and they're also loading up this text projection head. And the temperature is nothing but it's just a variation of the like this. It's controlling of the projection, how much you want to do it. So if you go into this particular forward output, what it will do is it will take up this image, it will extract the feature, it will take its respective text, and it will pass into a text encoder, right? So you have image and text features, but these are of different dimensions. So we want to convert into the same dimension. So what they will do is we'll pass this image features and text feature to the projection. So this projection will compress that particular image features and the text feature into a similar dimension. So now this particular embedding will have same dimensions. Once we have the same dimension, now we can calculate the co-similarity, because to calculate co-similarity we should always have a single dimension, right? So that's why they are doing it. Now this is the calculation part that I've been talking about the contrastive loss. So let me go through it. It will be very clear here now. So once we have this image embeddings and text embeddings, what they are doing is they are trying to calculate the dot product between these two, right? So this is a text embedding and this is the image embedding. So now this text embedding will have the image, the text of the image, and the other text also, like itself and other images text as well. Similarly, this image embedding will have its self image as well as the other images as well. So that's how we're going to calculate the logics. And now this will also calculate the image embedding and image embedding relationship. So they're also trying to calculate the relationship between the image to its image relationship and image to other image relationship. So obviously the dot product should be very high with respect to the same image, right? And similarly, we are going to calculate the text embeddings and its other text embeddings dot product. So we are trying to bring the text embeddings closer to each other by learning the text embedding from its text embeddings and with other text embeddings. So that's how we are trying to calculate the image similarity and the text similarity. And once we have these three things, we're going to calculate the targets, right? So this target is nothing but we are this is what the target is, right? So targets are nothing but the label that I talked about here. If you see, these are labels, right? So this is what we are trying to calculate, how we are justifying the targets, how we are calculating the targets, how we are making the targets here, because we don't have the targets here. We are trying to make the targets by own. It's a self-supervised learning, but we are also trying to calculate those targets. By making the targets only we can learn, right? So um, the importance of this image similarity and text similarity was the calculation of this image similarity and text similarity was there because of this only, because to calculate the targets, to label. So in this softmax function, we are trying to average out this text similarity and image similarity, and we are going to get the targets, right? And once we have this target, that is the label, now we can calculate text loss and the image loss. And the text loss and image loss are very much similar. We are trying to pass the cross entropy. We are trying to use the cross entropy, and we are passing the losses that we have calculated and the targets. These are targets. And for the similarly for the image loss, we calculate the cross entropy and logistics and targets. And that's how we are going to calculate text loss and image loss. And then finally we are going to average out these particular losses, and then we'll return the mean of this particular loss. That's how we are trying to do it, right? So this seems to be very complicated here, but it's very easy if you just try to explore it out. It's very easy to understand. We're just trying to calculate a similarity between the positive samples, and as well as the cosine similarity between the other negative samples. So this is what actually it is. It's nothing but it's just taking up the positive samples relationship and negative sample relationship. It's like a triplet loss that we're trying to calculate, right? So it's just a different way of saying the triplet loss, because in triplet loss we always have a label, but here we don't have a label, but we are trying to calculate the label by using this image similarity and the text similarity. So that's a different, that's only difference. Other things are very same, the data is same, and that's how we are calculating it, right? So that's how the clip model has been defined. And now we'll just go to the training part. So here is just where we're dividing the data set to train and test. And now we are building up the loaders, like we are initiating the loaders, data loaders. And this is a training step and a validation epoch. You can just go through this. And this is a main function where we are going to learn about the things. And now we'll train this model by using this by running this particular main function. And once we have this main function ready, we can just run this particular main function. So before making of this particular video, I ran this particular code. So because it takes a lot of time to train, you can see it takes like 23 minutes to 24 minutes for a particular epoch to run. So I trained it already, and for this particular demo, and you can see the loss has converged to 0.431 in just 2 epochs. So let's just go through the like once the model has been trained, we will just go through the inferencing part, how the things have been learned, right? So we'll just uh, put up this function which will take up this embeddings of the particular images and the text, and it will generate embedding for us. So what this particular function will do, it will take the data set, whatever data set, validation data set, and it will take up the best model that has been trained, and the trained here, the model that we have trained here. It will take these two paths, and it will generate an embedding for the images, and it will also return the model. So once we run this particular code, we can use our uh, particular embeddings to generate to find the images, right? So this particular function help us to evaluate the model. So once we have loaded the embeddings and calculated the loaded the model in here, we can calculate actual matches. So we'll just pass this images, just pass this text to the model, and it will try to get the right images for us which are associated with this particular text. So what is actually it is doing is, we are going to pass this particular text like one dog sitting on the grass. So it will just try to find a image which is which is very close to uh, this particular text, or which has this similar meaning, which has similar meaning to this particular text. So it will just try to find out the images from the data frame, or from the data set, to extract the images of the similar meaning. So let's pass this, and you can see it has quietly extracted the things out from the images. You can see the dog is sitting on the grass, right? The dog's one dog. Uh, it's not a dog. It's a dog. So these are the things, how it is being doing. So it is actually finding a relationship between the text and the images, and you see how it is beautifully understanding the context of the image and the on the and the text, right? So you can use it, you can use the embeddings of this text and the image for your n number of cases. So this is one part of the use case that you can build up. So once you have this model trained, you can use it for the classifier models. You can use it for like, once you have this embeddings, right? Once you have this image and text embeddings, you can use it for classification models. You can use it for search engines. You can use it for like, you can use it for anything. So this is just the demo that I am trying to do is here is just kind of a search engine query. So you're actually trying to pass one query, and you're trying to generate some images, right? So you're trying to find the nearest images with this particular meaning. So this is what it is, right? So this is the clip model, and you are able to learn that both of the world of a language and the image into a single model, and trying to extract the better embeddings by using the image and its respective text, and get the better embeddings related to each other with the image and text. And then you can use those embeddings for your use cases, for your downstream tasks, like search engine, or building up a search engine, building up a classifier model, like n number of things there are. You can do it with this particular models. So I hope you like this particular thing, and if you understood this particular part, I know it's little complex to digest these things, but it's very simple to understand if you know the cosine similarity of the thing. So I hope you enjoyed this particular video. If you like the particular content, please do subscribe the channel. Thank you.